Namaste and welcome. Today we're doing something really cool. We're going to completely demystify the incredible journey of a single, solitary neutron. We'll look at exactly how it travels, how it interacts with atomic nuclei, and basically the physics that govern its entire path. It is, literally, a journey of energy, an Ujra ki yatra.
Here is our roadmap for today's itinerary. Aaj ka safar. We'll start with nuclear cross-sections, scale up to microscopic versus macroscopic targets, hit the 1V traffic jam, climb the resonance peak, explore inside the compound nucleus, and finally, wrap up with calculating reaction rates.
Okay, let's dive right into this. Section 1, Nuclear Cross-Sections, the target practice. So in the microscopic world, everything revolves around hitting a target, right? Nishana lagana. To measure the chance of a neutron hitting an atomic bullseye, physicists use a unit called the barn. Now get this, it equals 10 to the power of negative 24 square centimeters. That is mind-bogglingly tiny. No way you can even visualize that. But mathematically, it perfectly represents the effective target area a nucleus presents to an incoming neutron.
Now you might be wondering, why on earth is a geometric area, a barn, used to measure atomic interactions? Aaiye jante hain. Let's see how this physical concept actually translates into probability.
Just take a look at the visual geometry here. You see those green circles? They represent the cross-sectional area, which we denote with the Greek letter sigma, of the target nuclei. But here's the catch. Rather than a solid physical block, this area actually represents a probability. Asan bashame, ye ek neutron or nucleus ke milne ki sambhavna hai. Simply put, it's the sheer likelihood of a neutron and a nucleus actually interacting as that neutron just flies right by.
Moving on to Section 2, Microscopic versus Macroscopic Targets, Scaling Up, because now we really need to zoom out from that single target. And this brilliantly illustrates exactly how we do that. Up until now, we've just been tracking a single neutron. To zoom out to an entire block of reactor material, we bridge the gap using n, which is the atomic number density. By multiplying the atomic density of the material by that microscopic cross-section we just talked about, little sigma, we get the macroscopic cross-section, capital sigma. This basically gives us the probability of interaction per unit of path length traveled.
Which brings us to Section 3, the 1V traffic jam. Dhimi gati, zyada prabhav.
So what actually happens when our traveling neutron slows down and enters the thermal range, below 1 electron volt? Well, we enter what's called the 1/V region, and its wild but slower neutrons actually have higher absorption probabilities. Think of it like a slow car stuck in a traffic jam. The driver has way more time to look into a specific store window. Similarly, a slower neutron spends much more time hovering near the target nucleus, drastically increasing the chance of an interaction. The cross-section is literally inversely proportional to its velocity.
Okay, Section 4, Hitting the Resonance Peak, an Anand Kachal.
Now, what's really interesting about this is that the journey isn't always just a smooth, predictable slope. Suddenly, in the resonance region, specific energy levels take over and dictate the interaction. As the neutron's energy shifts, it can hit these specific quantum energy levels. And when its kinetic energy perfectly matches the energy required to raise the nucleus to a quantized excited state, boom! The cross-section spikes drastically, governed by the Bright-Wigner formula. It's exactly like tuning into the exact right radio station, sahi frequency match karna. When that frequency matches perfectly, the probability of capture just shoots right through the roof.
Let's look at the aftermath in Section 5, Inside the Compound Nucleus.
So, once our neutron is finally absorbed, we form this highly excited, metastable compound nucleus. It's super unstable. To release that extra energy, it can take one of several different paths or reaction channels to decay. It might just spit a neutron back out with the exact same energy, that's elastic scattering. It might release one with less energy, inelastic scattering. Or it could undergo radiative capture, keeping the neutron and releasing a gamma ray instead. Or agar energy bahat zyada hoy, like really high, it could even result in multiplying neutrons, producing charged particles, or, undergoing full-blown fission.
But of course, in physics, there's always an exception, right? In magic or highly neutron-rich targets like calcium-48, this entire compound nucleus model just completely breaks down. It's fascinating. Because there are practically no excited levels available up to 1 mega-electron volt, the neutron actually undergoes direct capture. It completely bypasses all that typical resonance traffic and just slips right in.
All right, coming back up to the macro scale. Section 6, Calculating Reaction Rates, the Macroscopic World.
Let's move to how this builds into real-world applications. Transitioning back to the macroscopic world of a working reactor, we have to somehow calculate total reaction rates across literally billions of events. Obviously, we can't calculate trillions of individual neutrons flying around at various speeds one by one. That's where the Maxwell-Boltzmann distribution comes in. It helps us find the thermal average of all these chaotic interactions, beautifully smoothing out those extreme resonance peaks and the 1/v curves into a usable, thermally averaged cross-section velocity.
So the crucial point here is this equation. Reaction rate density R equals the total neutron density times the target density N times that thermally averaged cross-section velocity. This incredibly elegant equation finally gives us the total number of reactions happening per unit volume every single second. It is for sure the ultimate mathematical bridge between the highly unpredictable quantum realm and the measurable, physical world of an actual nuclear reactor.
But, our journey doesn't fully end there. As we push to higher, unresolved energy regions, those distinct resonance peaks start to overlap, and honestly, our clean mathematical models just start to break down. Hum आगे क्या discover करेंगे? What secrets still remain hidden in all that high-energy chaos? The exploration of the quantum realm continues, and honestly, that is exactly what makes nuclear physics so endlessly captivating. Keep exploring.